hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, in this module we are discussing various aspects of space radiation environments, and we have seen the different phenomena as for example, the linear energy transfer, then total ionization dose, then displacement damage and single event effects. In fact, in the last session we explained what is single event effects. So, as you remember, we mentioned that the single event effects are caused by a single energetic particle of very high energy. It can be of several hundreds of mega electron volt or even the giga electron volt, and it can be also a quanta of the radiation. So, we explained different types of the single event effects. The first one we explained, it is single event offset or SEU. So, as you remember, we said a single event offset is a soft, it causes a type of soft error in the memory devices by flipping the bit. So, which can be corrected. The other type we discussed, that is the single event latch up, and as you have seen in this type of facts, there is a we took an example of the CMOS circuit, and there we have seen because of the parasitic elements of the PNP and NPN, the bijunction transistors and forming a SCR. So, it gets a when the feedback loop the gain is more than 1. So, you get a feedback current which causes some sort of a short circuiting current, and because of that you are having a single event latch up. So, single double event latch up, even when that source is when there is no radiation exposure, still that thing will continue. So, that is why we called it a hard error, but in these two types of errors there is no physical damage. The third type what you consider, that is the single event burnout SEV. So, there the high energy particle causes a physical damage, it can be the melting or the burning of the component itself. And the fourth one we explained, that is the single event gate rupture. So, what is the gate rupture here? So, it can be the CMOS gate. So, where the metal oxide is used just below the gate. So, that dielectric, that is the metal oxide layer, it can have a breakdown or the rupture because of the incident of the energetic radiation particles. So, we explained all those things, and whatever we discussed like the displacement damage or the ionization, that is total ionization dose, we will summarize all this thing when I discuss the effect of those phenomena on our or this radiation effects on the spacecraft bodies as well as the astronauts. So, we will consider the space radiation both these effects, that is the space radiation effects on the spacecraft and space radiation risks to astronauts, and we will take the cases of the IIS to explain what is the radiation environment there and how that radiation environment affects the health of the astronauts. So, since we are summarizing here, we will again we will just revisit the types of the space radiation which affects the spacecraft and the astronauts. So, as we already explained, that is the galactic cosmic rays GCR. So, GCR consists of high energy particles, it can be the atomic nuclei or it can be very heavy ions, and it comes from the outside the solar system. The second event which is of which also the affects the spacecraft and the astronauts, that is the solar particle events. So, this is caused by our the sun activities, whenever there is solar maximum or in the event of the solar flare or the strong coronal mass ejection, you can have this type of solar particle events, where the particles from the hundreds of mega electron volt can be emitted from the sun's atmosphere, and this is this consists of the protons and heavy ions. Then trapped radiation belts, that also we discussed in detail. So, these are the electrons and protons, and the electrons are predominantly found in the outer radiation belt, whereas the protons that are trapped in the lower or the inner radiation belt, that is the Van Allen belts. So, these are the three the sources, and whatever this we told about the different types of these phenomena which happens, these are caused by this either by all three or different effects. It will depend again on the what is the energy of the radiation. So, again these three this environment, whatever we said, that is the three sources of the radiation, they also it is a function of the Earth's orbit. So, when you consider the low Earth orbit, so low Earth orbit, it is 160 to 2000 kilometer, that is defined as the low Earth orbit. So, here this low Earth orbit is shielded by Earth's magnetic field. That is why we can consider that is the the direct effect or the effect will be lesser as compared to this medium Earth orbit and high Earth orbit. So, medium Earth orbit, it is 2000 to 35,786 kilometer, that is given by the geostationary or geosynchronous limit. So, this is because of the near radiation belts. So, because of that, there will be the possibility of higher radiation exposure. And the third one is the geostationary orbit, or it can be geosynchronous orbit, and these are within the outer radiation belt. So, there is the possibility of very higher the proton flux. So, it means that the radiation environment, the severity of the radiation environment is with the high Earth orbit as compared to the low Earth orbit. When we go beyond the geosynchronous orbit, that means it is the interplanetary space, then there is the intensity of the GCR and the solar particle event, it increases, and you are having the higher on the intense radiation exposure. Now, we will see what are the effects, especially on electronics. This topic already we have discussed, but now we are as a total we are discussing all the effects. So, first we will see what is the effect on the electronics. So, as already you have seen, this effect is the single event effects, that is especially it is relevant to the semiconductor devices, and electronics is basically it is the semiconductor, all the devices are the semiconductor devices, and already you have seen what are the things, single event effects. It can be upsets, it can be latch ups, it can be burnout, or it can be gate rupture in the microelectronics. So, what happens, the energy of radiation particles that cause single event effects typically ranges from a few mega electron volt to hundreds of mega electron volt or even higher, it can be even the giga electron volt, depending on the type of the particle and the device sensitivity. Type of the particle, again it will depend on what is the source, whether it is a galactic cosmic rays or whether it is the solar particle events. So, depending on that thing, it will depend what is the energy of the that impingent particles. The heavy ions of galactic cosmic rays with energies which can be around 10 to 100 mega electron volt per nucleon are essentially effective at causing the single event effects. because they deposit a high amount of energy in a small volume, because it is a single particle. So, the volume which is affected by this energetic particles, instantaneous this interaction, that happens in a that is that is the energy transfer in a very small volume. So, this is one reason why the single event effects happens in the spacecraft semiconductor devices. The other source is the solar energetic solar particle events, SPEs. So, this again it consists of protons, alpha particles and heavier ions with energies usually in tens to hundreds of mega electron volt per nucleon range. So, both the SPEs and GCR, they are having the effect almost the similar, only thing is that the GCR has the possibility of higher energy, it can be in the giga electron volt. Then also we have seen that there can be displacement damage. So, displacement damage is not a ionizing type of damage, but it is basically a physical damage to the lattice structure of the semiconductor. So, this typically requires particles with enough kinetic energy to displace the atoms. Those atoms it can have a few tens of electron volt to kilo electron volt per collision site, but the incoming particle which causes the displacement damage itself, it has to be in the range of kilo electron volt to mega electron volt. Of course, for the displacement damage, the intensity of the energy is lower, which causes the single event effects. So, displacement damage it can be it is generally it is caused by the solar particle events and the Earth's radiation, that is the particles in the Earth's radiation belt. So, these two are important. So, you have seen that here we are not talking about the GCR. So, if the GCR, that is the galactic cosmic rays, they causes mainly the single event effect. Okay. So, we will again continue with this effect on the spacecraft electronic devices, and then the total ionizing dose. So, by total ionizing dose, we understand it is the gradual degradation of the electronic components, whereas the other two cases, especially the single event effects, it is not the gradual. Whenever a particle is incident and then that particle creates a ionizing path, but here it depends on the what is the it happens gradually. It can be the throughout the life of the operating life of the different components in the spacecraft. So, here the energy range for the space radiation particles causing the TID for electronics, they typically the electrons with energies from about 100 kilo electron volt up to a few mega electron volts, it contributes significantly to the total ionization dose, and this type of electrons which we just told about the energy range, that means from 100 kilo electron volt to a few mega electron volt, they are these are available in the Earth's Bannon radiation belts. So, mainly the TID is caused by the trapped that is the particles in the trapped radiation belts. Next is the first we discussed about the electrons, now the protons. So, protons with energies that which ranges from 1 mega electron volt up to a few hundred of mega electron volt, they contribute to TID. Lower energy protons which are less than 1 mega electron volt are usually stopped by the spacecraft shielding, that already we have seen. So, there is a the stopping range. So, it again depends on the material thickness. So, if the energy of the incoming radiation particles, the protons are, it is less than 1 mega electron volt or it can be less than 100 kilo electron volt, then those will be stopped by the spacecraft shielding, if proper shielding is used, proper thickness is used, and those will not contribute much to the TID. So, it is needed that the range it should be, the range should be that is it only in the lower energy range it can happen the TID. And while very high energy protons which are greater than 100 mega electron volt, they penetrate deeper, that already we have seen. Of course, their fluxes are lower, and if it is more than 100 mega electron volt, already we have seen that causes the single event effects. The third type which causes the TID, it can be heavy ions. Heavy ions generally contribute, but of course, it contribute less to TID, and those can cause the displacement damage and single event effects instead. Now, we will see, we have seen it, that is the effect of radiation on the electronics, especially the semiconductors. They have the effects on the the polymers and the metals, and the metals are used for as a for the shielding of the radiation. So whenever this shielding material, that is, are exposed to the radiation dose, they can make this the shielding material, that is the metal, brittle and fatigue, and because of these, the shielding materials, they face swelling and cracking over time, because it become brittle and fatigue increases because of this effect. Now, already when we are discussing this spacecraft material, you have seen that a lot of polymers and composites are used, and this when it is exposed to the radiation. So, the chain session means that is the breaking of the that is the polymer molecules, or this is the chain of molecules into smaller fragments, and it can cross link from ionizing radiation. So, these are the effects of the radiation on the polymers, and because of this, it loses the mechanical integrity and the flexibility, and the optical properties degrade. As for example, whenever these materials are used as thermal blankets, so because of the thermal blanket means it should be able to act as a radiator, but because of the because of this radiation impingement, what happens, the material properties, the mechanical or the thermal properties of the material is changes. So, that is why the properties, it is like the radiation properties, what is the absorption and the emissivity, all these changes. And the solar arrays also, solar arrays it is that it works on the photovoltaic effect, and because of this radiation, that the semiconductor properties they degrade, and because of that you are having the degradation in the optical properties. Now, the coatings, now the several types of the thermal coatings and protective coatings are used. This can be thermal control or anti-corrosion. So, those may degrade, and there the peel strength also gets reduced, it can peel off. Semiconductors already we have discussed, that is the displacement damage, then it can be because that is the ionization, which will cause the leakage current and shifts in the device parameters, and then single event effects that already we have seen that can cause soft or the hard error in the digital logic devices, or it can have this spike, it can create some noise spike in the analog semiconductor devices. Solar panel efficiency reduction due to radiation damage, that already we have discussed. Now, we will see the radiation exposure orbit wise. So, we will see the radiation exposure of the spacecraft in low Earth orbit. So, Earth magnetic field, already we have said Earth's magnetic field provides partial protection, but because of there is a region where the radiation belt, that is the height of the radiation belt, it got reduced. So, that is called the South Atlantic anomaly SAA. So, the South Atlantic anomaly is an hot spot of the trapped radiation, which is there at that the height or the altitude at this region, it reduced by 200 to 250 kilometers, it comes towards the earth. So, we will see that there are some the mission, some spacecraft they can cross the South Atlantic, that is the region of this SSA. So, we will see that. And here the radiation impact is moderate, that we have seen because of especially this strong Earth's magnetic field, but it is critical to that is international space stations and low orbit satellites, because of the presence of the that is the trapped radiation belt at the SSA region. Okay. Now, this the trapped radiation belt Bernard-Mers, so it lies just below, because this radiation belt, if you see the inner radiation belt, it starts from about 1 radius of Earth to about 2 radius of Earth. So, it may so happen and at that SSA, this is still it is reduced by 200 to 250 kilometers. So, there is the possibility that there can be some satellites, or we will see that even ISS also comes very near to this region. So, this gives you an exposure to the trapped radiation belts, and mainly this low this is inner radiation belt, it is predominated by the trapped protons. So, those protons can be of it can create the radiation dose. Okay. So, this already I said, that is the SSA is a region where the inner belt comes closest to the Earth, increasing the radiation exposure there. Then galactic cosmic rays, of course, its effect is much lesser here. So, it is less shielded in low Earth orbit compared to Earth's surface, but attenuated by Earth's magnetic field. Then solar particle events. So, here again the burst of high energy particles, mainly protons from the solar flares and coronal mass ejections, can cause sudden intense radiation increase in LU. So, it is possible to have, because of the whenever this happens, like solar flares or coronal mass ejections, there can be very high energetic particles coupling through the polar cap. So, again it may create whenever we are operating the satellites at very high latitudes, it can happen like that. And it is very clear that is this intensity of this solar particle events, its intensity varies with the solar activity. So, during the solar maximum, even low Earth orbit can be dangerous or can be detrimental, the radiation environment can be detrimental to the spacecraft. So, here it is lower, the dose rate is lower than higher orbits, and it gives significant the Earth's magnetic field, it provides significant shielding. And this radiation level, whatever we are seeing the LU, it again it varies with the altitude and then latitude also, because whenever you are going to the polar region, then this intensity may increase during the solar maximum, and also of course, it is a function of solar activity. This already we discussed about the South Atlantic anomaly. So, spacecraft material, it reduces exposure, but secondary radiation can contribute to dose. So, whenever the spacecraft material, it can shield it, but because of the secondary radiation, you have seen there can be secondary radiation because of that Bremsstrahlung radiation. So, those particle, like it can be X-rays or gamma rays, that can also contribute to the dose. Yeah. So, the secondary particles already I said. Then the radiation exposure to medium Earth orbit and the geostationary orbit. Since the medium Earth orbit, it passed through the Van Allen belts. So, there is there can be intense particle flux, and the geosynchronous or the geostationary spacecrafts, they are constantly exposed to high energy protons and electrons. So, as I already said, the severity is more, that is the radiation environment, the severity is more in high Earth orbit. So, you need this enhanced radiation shielding and the radiation hardened electronics. Now, we will see, now we have seen this is the effect on the material. but let us see what is the risk to the astronauts, what is the the radiation effect on the human body. So, the International Space Stations is in low Earth orbit, it is 400 kilometer altitude, and it is protected partially by Earth's magnetosphere, as we already said, but it is still exposed to the space radiation. And the average radiation dose to astronauts it is received, it is around 150 to 200 millisievert for 6-month mission. Radiation varies with solar activity, that already I said, and the position in orbit where it is. So, whenever it passes through this region South Atlantic anomaly, the exposure will be more there. And in ISS the dosimeters, this is are used on board, and the what is the extent of the exposure that is monitored by these dosimeters. So, at an orbital altitude of around 400 kilometers, the ISS astronauts have the probabilities of exposure to higher fluxes of ionizing radiation, because this 52-degree orbital inclination of the International Space Stations causes it to pass through the SSA, that is South Atlantic anomaly, daily. And this region is located east of Argentina, and it is characterized by anomalous perturbations in the Earth's magnetic field with trapped energetic particles which are found in the lower altitudes. So, because of this the astronauts are subjected to higher fluxes of ionizing radiation, and there can be these sources of the galactic cosmic rays, energy particles outside our solar system, and particles trapped in the Earth's magnetic field. So, higher energy protons and heavy ions, this emanate from the sun elsewhere in the cosmos. Okay. So, this energy that is higher energy secondary particles that we have already discussed, which are produced when incoming radiation strikes this spacecraft hull, and this can also increase the radiation dose. So, the average total dose of radiation that a person on earth receives from the natural land based sources and the medical procedures, that is less than 5 into 10 to the power minus 3 sievert per year. But at the orbital altitudes of the space station, that already we said this is around 0.3 sievert per year. And so, astronauts who fly missions solely in low Earth orbit unlikely to receive a total dose of 1 sievert over their career. But when the duration of the space flight becomes longer, and as the destinations take us further from the Earth, the radiation doses will become higher and higher. So, this astronauts participating in exploratory missions to Mars, they receive an estimated round trip dose that of around 1 sievert. So, with this I will conclude it here, and we have discussed all the effects of the radiation environments, and in the next session we will discuss how we can model this radiation environment, what are the mitigation techniques, what are the design guidelines. Okay, thank you very much.